Well, hello everyone. Welcome to the series, Viewing Multidimensional Poverty from Many Angles, which is coming to you today from the George Washington University in Washington, DC, from Oxford University in Oxford, UK, and the United Nations in New York City. I'm James Foster, the Vice Dean of the Elliott School of International Affairs at the George Washington University, representing the Institute for International Economic Policy, or IIEP as we call it. I'm here with Ricardo Nogales and Jacob Dirksen of the Oxford Poverty and Human Development Initiative, or OPHI, in the Department of International Development of Oxford University. And along with our colleagues, Yanchen Zhang, Heriberto Tapia of the Human Development Report Office of the UNDP, we're pleased to offer this series on the Multidimensional Poverty Index, or MPI. How it can be used in theory and in practice to support development goals and to guide policy. In today's episode, the fifth in the spring or Hillary term, Mauricio Gallardo of the Universidad Católica del Norte in Chile will present Measuring Vulnerability to Multidimensional Poverty with Bayesian Network Classifiers, with discussion by statistician and econometrician Stefan Sperlich, of the University of Geneva. In just a moment, I'll ask Ricardo to describe the series and to introduce the speakers. But first, I'd just like to express my appreciation to our IIEP, OPHI, and HDRO colleagues, and especially to the donors and funders who make this work and the series possible. Here at the Elliott School, we're especially grateful to the IIEP Executive Circle, who under the leadership of Deborah Lair and Frank Wong have allowed the Institute to ramp up its activities during the pandemic, creating new research, helping educate the next generation, and reaching out to the policy community through events like this one. After last week's busy week, which featured events on multidimensional poverty in Brazil, on the conflict in Ukraine, on Black politicians in the US, on poverty dynamics in India, and several others, this week is relatively quiet, leading into our spring break here in GW. Next week, are we going to have an event? Kyle, give me the latest for Jacob.
Jakob, over to you.
I don't think we will have an event next week, but we might have another one later on. We'll keep everyone posted on our websites and via email if you've subscribed to our newsletters.
Fantastic. So next week, I presume that due to spring break, we'll all be off, or at least that's our spring break, so I know I'll be off. If you miss any of the events that went before or anything in the future and want to see it online, go to IIEP's YouTube channel at IIEPGW. Now, let me turn it over to Ricardo, who will introduce today's speakers and talk a little bit about the series. Ricardo.
Thank you very much, James. Good morning, good afternoon, good evening, everyone. Thank you very much for joining this session. And as James was saying, so this whole series is devoted to understanding and analyzing multidimensional poverty and multidimensional well-being from different angles. And that, of course, entails several aspects and several views and several disciplines. The reason why these three institutions combine and join forces to come up with this series every week is the fact that you need to have this multidimensional lens to understand multidimensional poverty and well-being. From a policy side, it is very much useful and important that policymakers not only understand, but also are active part in whatever method or technique we have to understand this very important social issue. But as academics, from a more methods and a more academic-oriented viewpoint, we need to understand and improve always and learn from each other from methods and ways of improving the way we understand things in this complex issue. So in this session, we're going to have we're going to derive a little bit more to the method side, and we're going to have the pleasure, as James said, of having Mauricio Gallardo as presenter, who is an associate professor at Universidad Católica del Norte in Chile, where he teaches econometrics and statistical methods. He holds a master's in economics from Pontificia Universidad Católica in Chile, and a PhD in economics from Universidad Nacional de La Plata in Argentina. Before entering the academic world, he worked for the statistical division at the Central Bank of Chile, and he's also worked in providing technical assistance to several international organizations, and his research mainly focuses on the analysis of poverty, vulnerability, and inequality of opportunities. Discussing the interesting work that Mauricio is going to present us, we have one of the, I have to personally say that it's a personal, I admire this professor very much, Professor Stefan Sperlich from the University of Geneva, where he teaches econometrics and statistics. Professor Sperlich has a PhD in economics from Humboldt University in Berlin, and he also holds a diploma in mathematics from the University of Göttingen in Germany. He has held appointments as chair of econometrics and statistics in Universidad Carlos III de Madrid and University of Göttingen before going to the University of Geneva, where he has been since 2010. He has, among other things, been the co-founder of the Research Center on Poverty, Equity, and Growth in Developing Countries at the University of Göttingen, and is a research fellow at the Center for Evaluation and Development in Mannheim, Germany. He has published in several top-ranked journals in different fields and has been awarded the Koopmans Econometric Theory Prize, among others. So without further ado, let's start, please, with the presentation by Mauricio. Mauricio, the microphone is yours.
Okay. First of all, I would like to thank the OPHI and the Institute for International Economic Policy at George Washington University for inviting me to present my work. I'm going to share the screen. Okay. There is only one thing we can be sure about today. We live in a time of great uncertainty. As you know, several events in course are showing us the fragility of our life and our civilization. The COVID-19 pandemic, the consequences of climate change that we are already experiencing, the massive people migration, the current war in Ukraine. We live in a time where millions of people are threatened to fall into unemployment and impoverishment. That is, we are vulnerable. And our vulnerability is multidimensional. We are vulnerable in several aspects. This is why the research on vulnerability is now so important. I would like to mention only that vulnerability is a controversial concept. Even vulnerability to income poverty is a controversial concept. And there is extensive literature on this issue, and still is still a subject of debate. I am not going to spend more time in explaining the concept of vulnerability. I suppose the audience is familiar with this concept. If someone wants to ask specifically about this concept, I can answer after that in the time of question and answer. The problem that was faced in the paper that I am presenting now is the problem of measure vulnerability to multidimensional poverty. This problem is even more complex than the problem of measure one-dimensional vulnerability. However, some alternative approach have already been proposed to solve this question. The current practice is using an extended poverty line approach. As you know, the global MPI use a multidimensional cutoff of 32% for poverty, and in between 20% and 32% for vulnerability. Professor Calvo has proposed a solution that extends the Calvo and Dercon approach to the multidimensional space. However, this solution requires panel data, which are usually not available in the developing countries. Abraham and Kavey proposed to measure multidimensional vulnerability using a fuzzy approach of multidimensional poverty. And there are also two alternative methods proposed based on probabilities by using Probit or Logit models to estimate the probability of being multidimensional poor or the probability to be deprived in each welfare dimension. If we are looking for a method based on probabilities, the question emerged about what probabilities to estimate. Fenny and McDonald suggested estimating the probability of the aggregate, that is, the probability of being multidimensionally poor. However, the composition of deprivation could matter. The risk of being poor for a household deprived in health and employment is not the same as for another that is deprived in housing condition and access to basic service. As alternative, I suggest estimating the probabilities of the components, that is, the probabilities of being deprived in each dimension, and then using the Alkire and Foster counting method in the aggregation stage. Focusing on the specificity of the risks in each welfare indicator could help to refine the prediction of probabilities by component. However, this alternative could also have a shortcoming, taking into account that each Probit or Logit model does not give us a perfect estimate. When we have a separate model to estimate each component, we will also be adding the inaccuracies of each model estimate in the aggregation stage. But in addition, both Fenny and McDonald and I, in my work of 2020, used one-dimensional models, that is Probit or Logit models, to solve an estimation problem which is multidimensional in nature. Given this situation, our research question arises. Instead of using model focused on estimation of a single probability, that is unidimensional models, why not better use a probability model specially designed to represent the relationship between multiple random variables? These models are widely used in other fields of knowledge, but are not common in development economics and public policy. A first step was to estimate the Fenny and McDonald and Gallardo 2020 measurements of vulnerability using Bayesian Network Classifiers. We also tried to advance toward a new approach that could estimate both the probabilities to be multidimensionally poor, as well as the probabilities to be deprived in each dimension simultaneously. The tool we use to fulfill this purpose is a multidimensional Bayesian classifier named in PC. This tool allows to estimate all probabilities, both the aggregate and by component, simultaneously. In this paper, we are introducing the question about how we can measure vulnerability to multidimensional poverty using this multidimensional probability model. To be clear, I need to explain briefly what a Bayesian network is and how a Bayesian network classifier works. A Bayesian network is a multivariate probabilistic model which is defined through two elements: a directed acyclic graph G, which is shown here, and a vector of probability parameters. Here we have a directed acyclic graph as any Bayesian network graph, it is composed of two elements. The nodes are these three cycles. Each node represents one random variable. In this example, we call H the hypothesis. This is the multidimensional poverty status with two stages, to be poor or to be non-poor. And we have two other random variables. E1 and E2 are the income and basic service availability statuses in the household with two possible states which are deprived and non-deprived. This is a simple example that allow us to understand the concept of Bayesian network. The arcs are the arrow in the figure. They represent the conditional relationship between the random variables in the model. As you see, each arc is signaling from one node to other. It indicates that the preceding node is the condition of the second node. That is, the arcs in this example indicate that the variables E1 and E2 are conditional on the variable H. The original node is called the parent and or the ancestor, and the nodes that the arrow point to are called the descendant. The vector of probability parameters theta are the probabilities that the conditional probabilities that are shown in this figure. A Bayesian network allows us to infer the probability of the hypothesis given the evidence, which is called the posterior. We are interested in the probability of the hypothesis given the evidence. And we do that by applying the Bayes theorem presented in this figure. We obtain this probability according to this theorem using three sources of information: the prior probability, which represents our initial belief about the hypothesis before observing the evidence, the likelihood, which is the probability of the evidence given the hypothesis, and the marginal, which is the probability of the evidence. Let us now return to our example. We are suppose we have the rule that a household is multidimensionally poor if it is deprived in both dimensions, in income and basic service availability. Suppose we are informed that the relative frequency of poverty in this population is 0.13. This will be our prior. The joint probability of E1 and E2 conditional on the hypothesis is our likelihood, and the joint probability, probability unconditional is the marginal. The relative frequencies in our sample are shown here. That is, we have the uncensored headcount ratio for income is 8%, and for basic services 9%. But now suppose that for household A, we have been informed that this household is deprived in basic service and non-deprived in income. How does this evidence change our belief about the hypothesis? Using the parameters of our Bayesian network and applying the Bayes rule, we can do the calculation. Here we perform the calculation, and we arrive to the solution that given this evidence, the probability to be poor for this household increases to 23%. Suppose now another case, household B. Suppose that we have been informed that this household is deprived in income and non-deprived in basic service. How does this evidence change our belief about the hypothesis? Similarly, we can do the calculation using the bias rule, and we can arrive to the solution that the probability to be multidimensional poor for this household increases to 87%. The Bayesian, not that as shown in this example, which composition matter. The probability of being poor is not the same when the household is deprived in one dimension or another. The Bayesian network estimated in the paper that I am now presenting are much more complex than this one. However, the logic is the same. What do we want to estimate? What do we want to estimate in this paper? YW is a binary variable equal to 1 if a person is multidimensional non-poor, equal to 0 otherwise. YA is a vector of binary random variables, each one equal to 1 if a person is non-deprived in the dimension I, equal to 0 otherwise. XI is a vector of household characteristics of all of them are categorical variables of all the characteristics. And ZI is a vector of community characteristic. All of them are categorical random variables too. Our goal is to estimate the following function using Bayesian network classifier. Function H1 draws the probability of being multidimensional poor or and non-poor from the household and community characteristic. This function is in the spirit of the Fenny and McDonald approach. Function H2 draw the probabilities of being deprived and non-deprived in each welfare dimension from the household and community characteristic. This function is in the spirit of the approach I proposed 2 years ago. And the new function, the proposal of this paper is related to function 3, H3. This function draw both the probability of being multidimensionally poor and non-poor and the probability to be deprived or non-deprived from all available information, including the deprivation. We estimated 3 Bayesian network models. A Bayesian network classifier is a Bayesian network of specific topology in which the class variables appear as the parent of the feature variables. The first model is the simplest Bayesian network classifier, which called the naive Bayes classifier. This Bayesian network classifier has only one class variable, in this case to be poor or non-poor, multidimensional poor or non-poor, while feature variables are independent. Model 2, presented in this figure, is a Bayesian network of a more complex topology. This is a multidimensional Bayesian network classifier. The difference, the feature of this model is that this is a classifier with multiple class variables which are drawn as the ancestor or conditioning variables with respect to the feature variable. This function allows to estimate, this model allows to estimate the function H2 presented before. And the third model, model 3, is other MVC that differ from the previous only because in its topology, there is a superclass variable. It is included, this variable is included as the grandparent with respect to the feature variable. This function allows to estimate, this model allows to estimate the function H3 presented before. The Bayesian Network Classifier allows us to estimate the probabilities to be non-poor and the probabilities of being non-deprived, which in turn are the expected values of the random variables of interest. I recall that for a Bernoulli random variable, the expected value is equal to the probability of success, which in our case is being non-poor or being non-deprived. However, in vulnerability to monetary poverty literature, for several researchers, the expected outcome is not sufficient for assessing vulnerability. We also must take into account a risk component. For several researchers, there are two sources of vulnerability: the expected poverty and risk. Here are some examples. For example, Ligon and Chester used the Jensen inequality as the risk component. Gunther and Hagen used a component of variance. Chihuahua and Weibel used the standard deviation as the risk parameter, and I used it before standard outside semi-deviation. For several researchers also, the relevant risk is not the downside risk. Vulnerability to poverty refers to the risk of an unfavorable outcome. Then the outward dispersion is not relevant for its assessment. This view was pointed out by Calvo and Dercon, who introduced the no compensation principle of poverty. This principle states that good states do not compensate for states of hardship. I propose to use the downside mean semi-deviation as the risk parameter. And for binary variables, this downside mean semi-deviation takes the following form. This is the standard semi-deviation. This is like the standard deviation, but also considering the downward deviation from the mean. And this is for binary variables, this is the formula where P is the probability of success. In our case, will be the probability to be non-poor or the probability to be non-deprived. Now I'm going to introduce the risk-adjusted mean that I use, which is equal to the expected value, discounting the risk, discounting a risk component. This concept comes from the Agrisac and Rusinski rule. This is the Agrisac and Rusinski rule, which in turn comes from the mean risk dominancy criterion. According to the risk mean dominancy criterion, one random variable is strictly preferred to another whenever it has at least the same mean and at most the same risk when one inequality is strict. However, this this criterion does not allow us to make all possible comparisons between two random variables. To solve this problem, Agrisac and Rusinski proposed this rule in which they introduce the gamma parameter, which is a mean trade-off parameter. And they also demonstrated that this rule is consistent with the second order dominance criterion. Here the R are the risk parameter. That is the risk adjusted mean. In this case, in the case of binary variable, is going to take the following form. The probability of success is the expected value. This is the standard semi-deviation, and this is the parameter gamma between 0 and 1. We can now present the identification rules that we applied in the paper. We applied for the Fenny and McDonald approach. According to Fenny and McDonald approach, a household is vulnerable whenever its probability of being multidimensional poor is greater than age, which is the multidimensional poverty headcount ratio. A household is highly vulnerable whenever its probability of being multidimensional poor is greater than 0.5. And it is relatively vulnerable whenever the probability of being poor is in between these two thresholds. According to the Gallardo 2020 approach, we first identified the vulnerability by each dimension. A household is dimensional vulnerable whenever its risk adjusted mean is less or equal to 0.5 in this application. After that, the Alkirian-Foster counting method is applied. A vulnerability score is calculated in a similar way as it is done with the deprivation score in the Alkirian-Foster measurement of multidimensional poverty. And then the household is identified as multidimensional vulnerable whenever the probability score is at least equal to the multidimensional of K. The new MVC approach proposed in the paper identifies separately the dimensionally vulnerable and the multidimensional vulnerable using the same rule of having a risk adjusted mean less or equal to 0.5. The vulnerable household are also classified as poor vulnerable and risk vulnerable. Poor vulnerable are those who have an expected outcome less than 0.5, and risk vulnerable are those whose expected outcome is greater than 0.5, but below the risk-adjusted mean. In the new MVC approach, we do not use the Alkirian-Foster counting methodology as in Gallardo 2020, but instead we directly use the probabilities to be multidimensionally non-poor to estimate the vulnerability gaps, using the probability threshold of 0.5. And then we use the FGT design in the aggregation stage. Using the subgroup decomposition property of the FGT indices, we also decompose the aggregate vulnerability into components, the poverty components and the risk component. We presented in the paper an illustrative example, which was implemented using Chilean data. Data are from the CACEN 2017 household survey, and from the also from the census. We used the CACEN survey for household characteristics. The CACEN the survey has a complex sample design stratified by by conglomerate of household location. Is a sample, is a survey of national coverage, and it is representative of all regions and most of Chilean municipalities. However, there are some municipalities to which this household survey is not representative. Therefore, the census data was used for community characteristics. The sample, the total sample, after filtering for the missing data, was of 67,820 households and 214,321 individuals. The reference indicator used was the official Chilean MPI, which is structured as shown in this figure. This MPI includes 5 dimensions: education, health, employment, and social security, housing and environment, network and social cohesion, and 15 indicators. Here I present the main results. This table shows the main vulnerability to multidimensional poverty estimates. The vulnerability headcount ratios are in between 0.31 for the Fenny and McDonald indicator and 0.37 in the case of the Gallardo 2020 indicator. We estimated this with gamma 0.8 only for comparison proposal to the other paper that I estimated before with Probit and Logit models. And we also decomposed the vulnerability, the aggregated vulnerability measures between poverty-induced vulnerability and risk-induced vulnerability. The last column shows the ratio of the vulnerability rate over the poverty rate, which in the case of Chile is in this application is 0.207. According to this result, for every 2 multidimensional poor people in Chile, there are at least, in the more conservative estimation, at least 3 vulnerable people. This methodology allows also to estimate vulnerability to poverty by dimension. This table shows the main measures of vulnerability by dimension according to 2 approaches: the Gallardo 2020 approach are in these 3 columns, and the MVC approach in this column. These results allow us to have a vulnerability assessment by dimension. We also decomposed the dimensional vulnerability between poverty-induced and risk-induced vulnerability. Thus, we can see in which dimension is more important the risk, in which dimension is more important the poverty component. In Chile, according to this estimation, there are some dimensions in which the composition between poverty and risk is more balanced. For example, in school attendance, schooling lags, year of adult schooling, child malnutrition, and health insurance affiliation. In other dimensions, this composition is more biased toward the risk component. For example, in child malnutrition, in access to healthcare, employment, social security, retirement, insurance, and equal treatment. To assess the predictive accuracy, the predictive performance of the 3 Bayesian network classifiers that were estimated, a 5-fold cross-validation exercise was performed. A K-fold cross-validation is a procedure usually performed in machine learning application for assessing the predictive performance of a classification model. This procedure involves partitioning the sample into k random subsamples. Then k minus 1 subsamples is taken as the training sample to estimate the classification model. The remaining sample, known as the testing sample, is kept out to later test the out-of-sample predictive performance of the model. After estimating the model with the training sample, the predictive performance is assessed by calculating the accuracy of the model in predicting the right class for the testing sample. To avoid possible samples selection bias, the process is replicated, rotating the training and testing sample. And finally, the average predictive accuracy of the k-fold cross-validation exercise is taken as a measure of the predictive model performance. As we see in this table, the measures of accuracy in predicting both the deprivation status in the dimension as well as the multidimensional poverty status are high. However, there are some dimensions that are more difficult to predict. For instance, social security and year of schooling, years of schooling and social security. Maybe because these dimensions are less determined by the current household characteristics. We also perform a sensitivity analysis of the predictive accuracy achieved by the Bayesian Network Classifier under different scenarios, different poverty cutoff, different weight configuration, and different MPI composition. We found that the accuracy of the Bayesian Network Classifier in general remain high. However, in the case of model 1 and 2, it is more difficult to predict accurately when the multidimensional poverty threshold, K, is lower. In this case, 0.15. Some concluding remarks. Bayesian network estimation strategies offer, I think these tools offer a good alternative to the traditional Probit and Logit model to predict the probability of being multidimensionally poor. But also, the MVC has the advantage of being multidimensional procedure to solve a multidimensional estimation problem. The new MVC approach proposed in this paper tries to integrate the advantage of the previous approaches in a unified framework by estimating all the probabilities together. This is the first published paper in the direction of using Bayesian network for modeling uncertainty in the sphere of multidimensional poverty. Therefore, there is much more yet to research and discuss in this topic. These tools could be applied, for example, in studying the dynamic of poverty. This work as machine learning tools. That is, we can apply it. We can train the Bayesian network with one data set, and then predict to other data with other data set in the future. This is very good. For policy purposes, it will be useful to apply these models, I think, for measuring vulnerability based on the composition of deprivation, and also to predict future state of poverty. Thank you very much for your attention. Excuse me, please, for my pronunciation, but I think that I achieved that to be understood by you. Thank you very much.
It was extremely clearly understood by us. Thank you so much, Mauricio. Now, let me turn it over to Stefan for your commentary. Thank you very much.
Yeah, thanks a lot for this invitation. And I enjoyed very much reading at least the two papers of Mauricio, the 2020 and the 22. And actually the first of all is I have to rerun a little bit the definitions he came up with in his 2020 paper in order to better understand what we are talking about. And well, this is here just a repetition of when you think of multidimensional vulnerability, then you start nonetheless from the one-dimensional vulnerability in the different dimensions. And he defined it in the following way, that you have the conditional mean of an outcome variable. Actually, in his 2020 paper, it could be any variable. Here it was really already the binary decision if you are poor, deprived or not deprived. Yeah, but originally it could be much more general, maybe even just income. Okay, and then he gave his risk factor definition. What is somehow the distance, the square distance in expectation and then square root, but only the downside distance. Yeah. And well, then certainly one could ask, if this is any variable, then what does it really mean? So because this is the distance to an average, a conditional average, and he used then, for example, linear mixed models that mean with random effects for each municipality. That would just mean that you have a certain distance in income to the average in your municipality compared only to the people with the same characteristics or features. And here we refer certainly only to those that we observed, X and Z. This is essentially what it is. And then you have other factors, this risk adversity, the vulnerability threshold, everything has to be chosen. This has certainly the conditional expectation has to be estimated. Yeah? And while the Y has to be defined, and in the 2022 paper, it's clearly just the binary response, deprived or not deprived. Well, then the remarks is that this sigma is not related to standard errors. It is something, well, I would like to make this disappear, but it doesn't allow me. So I have to go back to the other code. So it's not related to standard errors of our estimates. Okay, it's a new definition of something. And that means that this expression, or our definition of vulnerability, has not a clear or a clean probabilistic interpretation. Yeah, it's a definition how we define vulnerability, but it's a technical definition. There is no probabilistic interpretation here. Well, and if you go then up to the multidimensional vulnerability, it's even a little bit, well, you can say worse or even more complicated. Yeah, but I don't know how to avoid this. No? Where this G is the indicator if you are vulnerable in a dimension or not. And then you look at the weighted, where you have to choose the weights, average, and then again, you compare it with a threshold. Okay. Okay, what is new here in the 2022 paper compared to before is so far he used, as he said Logit and Probit, but actually Mauricio did much more clever thing. It was not just Logit and Probit you used. You used generalized linear mixed models, which are much better for predictions than just a Logit and Probit. Okay. Nonetheless, it certainly has various implications, which he no longer has when he switches then to non-parametric prediction. What then the Bayesian network is basically a non-parametric prediction. Predictor. Well, then if you, however, try to estimate or predict much better this conditional mean, and now imagine you throw in many more features of an individual so that you can almost individually identify this guy, yeah? Then certainly a non-parametric estimator will perfectly predict the outcome. What basically means that this is almost zero. And then certainly this interpretation gets lost. So you wouldn't use anymore this measure, okay? Nonetheless, still many things, all the weights, etc., have to be chosen. So coming then more closer to his new paper, the 22 paper. Okay, so we say now, well, nonetheless, why not estimating or predicting non-parametrically this conditional expectation? Because this was the main motivation on the first slide, where he said, well, if we make an error in this estimation, then we carry on with this error in all the aggregations, etc. And he has chosen here the Bayesian network for classification as one possible non-parametric estimator. One could have gone one step farther and say, okay, if we try to be much more data-driven, much more in the direction of machine learning, so why not also doing this regarding the definition? So why not rethinking the definition of vulnerability in order to gain interpretation, to have a clear, let's say, probabilistic interpretation of vulnerability? Yeah. So one could have considered both challenges. Yeah. So, and the paper basically considers the first one, challenge. And then at the end of the paper, I would say he did not really much, well, a little bit, yes, no, H1, the model 1, also tries to go beyond just replacing the estimation of μIM. We will come back to that. So what are the implications of using Bayesian networks? Well, you could have taken any other. A drawback is definitely that you have to classify everything. You have to classify the X and the Z. You have to classify the Y. You must take binary responses. You really have to stick on the decision already if we deprived or non-deprived. So you potentially lose a lot of information. On the other hand, this at the same time offers you also an advantage, because now then if you have a binary response, then this risk factor has a much better and easier to interpret definition. Now it's just this expression where the PIM is a conditional probability to be non-deprived. Well, it depends on how you define it as non or deprived. Well, this is definitely an advantage, because also now it's no longer the risk that this is always zero. Yeah, okay, however, one could still ask, why not taking any other non-parametric estimator? Yeah. Well, also even here, if the classification of X and Z, that you must classify them even if you observe something continuous, is not necessarily a drawback compared to the former papers, because in the former papers you had a parametric linear model. Okay, now you have a non-parametric model. That means it's totally flexible. And if you think of just linear models, if you always want to use linear models, how do you do that? If you have a continuous X and a continuous Z, then you classify it. You transform it to many dummies, and then you include all these dummies in your linear model. This is the same thing as doing it directly in non-parametrics. So you can say, well, it's true, I could do even better. Instead of taking a classifier, I could take any non-parametric predictor estimator that allows for continuous variables, but at least I'm much, much better than just the GLMM. So much better at what we have done so far. Okay, now how do you compare then this, what you have done so far and what you do in the new paper? Well, actually then the model 2, H2, is really just replacing the generalized linear mixed model by the Bayesian network classifier. No? In the end, for H2, for model 2, this is all what happened. Well, but then in your paper, you go a little bit farther. You say, well, why not directly predicting the probability of a multidimensional vulnerability only using X and Z? So this is going beyond. No? And then you also say here you have model 3. And here it's not that clear to me. If you really estimate the probability of the all-over poverty using only the information about the one-dimensional deprivations, or if you actually use the predicted probabilities, or if you use Y and X and Z. This is not fully clear to me. So if you only use this information, well, then there were some some comments to be made, okay? On top of it, at least for this estimator, for the Bayesian network classifier, I cannot really see why you should get different results in your H3 for these probabilities compared to your H2. Actually, the outcomes should be exactly the same. It should be numerically the same because you do exactly the same estimation with exactly the same estimator and exactly the same information. So here and there, you should get the same thing. Okay. And as we can see, well, looking at all this, yes, you go beyond just replacing one thing by the other, by a more general, because you have this guy and you have somehow also this guy. But we don't really come up with a new approach to define a vulnerability that is more data-driven, that has really a probabilistic interpretation. We don't have that. You know? It's not, I'm not saying this is your fault and that you have to do everything in one paper. I just say this is something that came up to my mind. Okay, and then here we already have the last slide. So I could now ask why these Bayesian network classifiers. Yeah. So there are other estimators which are maybe more powerful, which also allow you to include continuous variables and to deal with continuous X, with continuous Y, etc. Okay, I directly give one answer to this. An advantage is these Bayesian network classifiers are very simple ones. And that means we can really estimate very well the standard deviations. Whereas when people come up with a neural network or something like that, then they have to simulate the standard deviations. They don't know them, okay? Here you can explicitly calculate them. So you really much better understand what's really going on and you know all the analytics of it, etc. Because in the end, what do we do? You are just thinking of probabilities. You are classifying the X, Z, and Y. And that means all what you estimate is you calculate proportions. This is all what you do. You calculate proportions. There is no complicated network of neural network or something behind. All what these guys are doing is calculating proportions and then multiplying proportions, as you have explained actually on your slides 12 to 14. Yeah. So if you take any other non-parametric estimator, your vulnerability index and decompositions, nothing would change. It would be exactly the same. So you could try others. Yeah. Then my question is, why didn't you do simulations? You only came up with an application, but an application is not that informative. It doesn't tell me how well this method works. Yeah, this is something you only find also with simulations. And when you already have started with simulations, then you will notice that there are different packages offer these Bayesian networks. Yeah? And if you compare them, do you really get always the same result, or is there some numerical problems with them in the implementation? Hopefully you always get the same result, no? But if you also find an implementation in Stata, I wouldn't be sure that you get the same in Stata as you get in R. And if the difference is huge, then there's some issue. No, this is one of the main problems today with these machine learning methods. You have to use the same computer, the same software, the same program to get the same result. Okay, and then this is just minor thing about your table 3. So when you talk about these results, no. This is table 2, table 3. So if going back to what I said, in general, I don't understand why you should get in model 2 and 3 different results. I think if you get something different like here, then it's only because you did a 5-fold cross-validation for comparison. So these differences are purely random. You should get exactly the same columns, except certainly the first line. But for all the rest, it should be the same, or they implemented something strange in the software. Okay, and then actually what is really interesting, I think, is then certainly okay. How much do you really recover what you observed? You know, because here this is comparison with the truth. Yeah, and in 84% you recover really the truth. Yeah. if you directly go, I'm only using X and Y without the one-dimensional information about being poor or not, then still 80%, that's a lot. But I wouldn't give too much importance to this number. Why? Because here, all what you do in the end is, going back to the slide, that the Bayesian network just recovers the final decision rule. You use already all the one-dimensional YIMs, yeah, and then you define, well, is this guy poor or not in the multi-dimensional way, yes or no. And all what the BNC recovers is the decision rule. What is nice to see that it can, but actually you wouldn't be too surprised. Okay. Okay, that's all.
Great. Stefan, thank you so much for the comments. Before I turn it back to Mauricio to address the comments he would like to address, anyone who's out there in the audience who has a question about interpretation, about technical interpretation, about policy interpretation, please feel free to use the Q&A function in Zoom. Mauricio.
Yes. Thank you very much for the comments. Of course, this is the first paper in this direction of using Bayesian network to estimate the multidimensional vulnerability, and there will be, of course, criticisms to this approach. I would like to say something about the semi-variance and about the semi-variance, because some comments were directed in this direction. What is the idea that is the idea to use measuring to introduce a risk component? The idea is that the risk is the expected value is not enough for assessing vulnerability, because the poverty component and the risk component will be different in different probabilities. In this, for example, in the case of if you use variance as the risk component, you are going to be identified as more to have more risk when you are in the probability of 0.5. Here, for example, your condition is determined by poverty, and also in the other extreme, your condition is determined by your high probability of being non-poor. But when you are in the middle, the situation is different. We need account for the risk in this area of the possible probabilities. However, the semi-variance move to the right because this is a measure which is asymmetric, and in the case of poverty on vulnerability assessment, we are interested in that one, only in that one, in the downside deviation. So here, asymmetric view is the problem with asymmetric view is that we are not interested in deviation above the threshold of 0.5. And when you introduce a risk parameter who is asymmetric, you add more risk to those who are over the threshold of 0.5. This is the idea that of using this risk parameter. I would like also to react that to another point. Why not use a model which is data driven? The problem is that we, to be honest, I avoid this kind of, I try to avoid more data to a model data driven because we need to compare. We need to compare periods. We need to compare between countries. And then I prefer a more simplified model. The selection of arcs, for example, could be using an algorithm, could be implemented by a special algorithm to select the arcs. But this also has the problem that it will be data driven. And when you design a Bayesian network, you have two alternatives. You can define the structure by using an algorithm and also by expert analysis. And in our general framework of multidimensional poverty, we have a structure as was in these models, in the model 2 and model 3. Regarding the difference, was another question about model 3. What information uses uses model 3 to predict the multidimensional poverty status? And yes, the prediction, once you have information, evidence, when you have evidence about the deprivation status, the information from characteristics is became not important. When you have evidence about in the second level, you just predict the third level. The discussant, it was right that when he indicated that the decomposition property is affected. Yes, it's affected because in this model we estimate separately the probability to be poor and non-poor, the probability, the multidimensional status, and also the separately the other status. Why are not equally the accuracy measurements? This is an exercise of a cross-validation exercise that is random exercises. But I am not sure if there is a little influence of the third level over the high level. And maybe this could affect the result of the accuracy exercise. Okay.
Okay, Mauricio.
Okay, yeah, okay.
So then we have a question that's actually there in the Q&A. It says, and this is from Hernando Grueso, who is a student who just passed his dissertation on a very similar subject. And he was just wanting to know whether, you know, when you're thinking about these probabilities, are they really the probabilities over an entire sample, or are you focusing primarily on the sample, the subsample that are the poor as you work through it? So that's one question that he had. And I'll say one other question that it may be a comment before you answer that. Yes?
Excuse me, James, I did not understand the first question.
He was just trying to see when he was applying this similar technique, he was thinking through, he would obtain certain probabilities that would be focused only on the poor themselves. Because in his case, for instance, he was very interested in seeing interactions between dimensions, if you will, among the poor. So to understand sort of links between being deprived in one and being deprived in another. And so he was trying to suss out here whether that kind of process, that interpretation of probabilities could be made given what you're talking about here, and whether it's only among the poor or whether it's among the entire population. So just, I've tried my best to represent the question. What's your best response to my imperfect question?
If I understand, he did an exercise of exploring what is only with the sample of poor, of multidimensional poor.
Yes.
But this is not, this is not, I think this is not right, because you need a random variable.
So therefore,
a variable with
it's when you calculate the probability of being poor or not, you certainly need the entire population. You cannot calculate it only from the poor.
Indeed. Indeed, I agree with that. It's just within the poor itself, then the question is whether one would, in his case, whether one would use the subset of folks who are poor or the entire population to think about a broader question, which is, I think, a very important one of interactions across dimensions.
But I think that will be better to explore the having the parents in this having a model in which similar to the example I showed with the illustrative example, a parent which has which is a variable with two status, poor or non-poor, and deprivation. This is very simple. You can do it only with charts, yes, and you can from this obtain a very interesting, maybe very interesting result, because the risk will be the probability to be multidimensional proof will be different according to the composition.
Indeed. So one final comment, which I'll make, and then I'll bring this all to a close. You know, throughout your discussion, you've been talking about downside risk. And indeed, when I did my original FGT paper, we were thinking about FGT2, the second measure, as being a measure of downside risk. Of course it is. And it appears in many, many situations now in terms of vulnerability. So it is quite interesting, the link between FGT2 and your measure, which was, of course, very similar to that, to the lower partial variance. I just think that there's a lot of interpretation that can be gained by thinking of things through that light. The other thing I wanted to mention was that there are many vulnerability indices that have been created designed to measure another form of vulnerability. It's related and distinct. That is vulnerability to the pandemic. And so looking under groups of people and seeing if a group of persons, due to their poverty status and all the other things that you're throwing about, might be more or less vulnerable to the pandemic, and therefore programs in Latin America in particular have been targeted on that basis. It might be reasonable to think through the relationship between what you're doing and what they're doing, and whether what you're doing can inform them or vice versa. And so rather than let you respond, what I'll do is then bring today's session to a close, and to thank our speakers for all their great insights. Really looking forward to seeing the next round of presentations after the break. Thank you so much. Please, people on the panel, go ahead and join up in the after event, which is listed in your chat. Again, see you all later. Have a great break from this series. Until next time, I'm James Foster here in Washington, DC. Bye-bye now.